Hi everybody, in this video we're going to explore higher order partial derivatives. So we've talked about first order partial derivatives before. The idea is that if we want to examine, for instance, the partial of some function with respect to x, then we fix y to be some constant and we can see what effect changes in x have on the value of the function. That is, at some point we can find the slope in the x direction. Or we can look at the partial with respect to y, in which case we fix x to be some constant, and we can examine the slope in the y direction, see what changes in y do to the value of the function. Well, we can talk about second order partial derivatives. For instance, we could look at taking a partial derivative with respect to x, and then with x, another one with respect to x again. And it's just like we might hope from what we know about single variable functions, that we're looking at how the slope in the x direction is changing as I change x. So we're examining the, say, concavity. We're seeing what's happening to the slope in that direction. And similarly for y, if we take two partial derivatives with respect to y, then we can see how the function value changes, how the rate of change of the function value changes as I change y. So again, sort of the concavity in the y direction. But since we've got two independent variables, we can also think about what are known as mixed partial derivatives. So if we take a derivative with respect to x, where we fixed y, and we look at how how changes in x affect the value of the function. But then if I take a partial with respect to the other variable, in this case y, excuse me, one way you can sort of imagine that is I'm looking at this slope in the x direction, and then what this mixed partial is telling me is then if I change where that cross section is, if I change my y value, how does the slope change at that particular x value? So first look at the sort of the slope in the x direction, and then see what changes in y do to that slope. And we can do this the other way as well. If I take a partial derivative with respect to y first, and then follow it with a partial with respect to x, the partial derivative with respect to y tells me what the slope is in the y direction for some fixed x. And then when I follow that with a partial with respect to x, I'm seeing what happens to that slope in the y direction as I change the x value a little bit, as I move that cross section right around that point. So let's look at an example. Calculating these is what you might expect. Whichever partial derivative you're taking, you just hold the other variable to be constant. So first we can find the partial derivatives with respect to x and y of this function. So take a minute to do that. I believe these are the correct appropriate partial derivative functions that we get from that. And then we can take further partial derivatives and look at all the second order partial derivatives and mixed partial derivatives. So pause for a moment to work these out, make sure you can find what these are. And I believe you should get these. And one thing to notice is that the mixed partials in this case were yielded the same function. We got there different ways. Taking the partial with respect to x gives a different function from taking the partial with respect to y. But then when I mix it up and take a partial with the opposite variable, we got the same thing out. So is that always going to be the case? Or did we just happen to pick some function that that works for, and in general it doesn't? Well, a little column A, a little column B. It turns out for nice functions, and by nice we mean continuous, there's a theorem that says that if those mixed partials are both continuous at some point, then they will be equivalent at that point. So as long as we've got continuous mixed partial derivatives, then they'll be equivalent. It won't matter which way you go to get there, what order you do your differentiation in. And it extends to higher order mixed partials nicely, so long as we're taking the same number of partial derivatives with respect to each variable. So, for instance, if these two partial derivatives are continuous at some point, then they'll be equal because they each involve one partial with respect to x and two partials with respect to y, whereas these two will not necessarily be equal because they involve different numbers of partial derivatives of x and y between the two of them. Okay, that's it. I'll see you guys in class.